So now we talk a bit about reaction selectivity, and here we can, for example, talk about chemoselectivity. And chemoselectivity means that one functional group of the molecule will react preferred to another functional group. For example, here we have two functional groups in the system. We have the Hep6-ene-2-one. And if we now want to reduce, then we know that this reaction will be chemoselective. And here we can, for example, only reduce the carboxyl group. So we end up with an alcohol, the Hep6-ene-2-ol, or we chemoselectively reduce only the double bond of the system, so we end up with heptane-2-one. This is one example how chemoselectivity can be explained. So in principle, you have two different functional groups, and then depending on the reaction, you can selectively change one functional group while the second will be maintained. The other kind of selectivity can be a ratio selectivity, and here we can say one position of a functional group within an unsymmetrical molecule reacts selectively over another. So for example, here the 2-methylpropene will end up with a major and a minor product, and these two products are structural isomers. So we can say then that we will get the selective formation of one structural isomer during this ratio-selective reaction. These are the first two types of selectivity, and for sure we can also have other types. So for example, we can have a stereoselectivity. And stereoselectivity means that one stereoisomer is formed selectively over another. So for example, if we want to reduce an alkyne towards an alkene, then we can start with this hex-3-ine, and if we use a Lindlar catalyst, then we selectively produce the Z-hex-3-ene. It means the hydrogen atoms are on the same side of the carbon-carbon double bond. Conversely, if we use sodium and ammonia for reducing this alkyne towards an alkene, then we end up with E-hex-3-ene. And here you can see that the hydrogen atoms are attached from both sides of the carbon-carbon double bond. And then very important is that the reaction can not only be stereoselective, but also stereospecific. And here you should always remember stereoselective means not the same like stereospecific. And stereospecific means that we have different stereoisomers which react different. For example, in this epoxidation reaction. So we have, for example, this cis or Z alkene, and then we do the epoxidation reaction and we end up with a cis epoxide. Conversely, if we start with the trans or E alkene, we will end up with a trans epoxide. So that means that both of the stereospecific epoxidation reactions are at the same time also stereoselective. And so this we can see here that cis alkene forms cis epoxide or trans alkene forms trans epoxide. And very important is that all stereospecific reactions are also stereoselective, but not all stereoselective reactions must be at the same time also stereospecific.